Howdy, Huskies. Welcome to section 6.3. We're going to split this up into 2 days, one day with algebra and one day with proofs. So we have all of our definitions here up on the screen. So why don't you hit pause and copy them all down. And then we'll go ahead and get this party started. Welcome back, sports fans. So let's go into all these really quickly. I think they're pretty self-explanatory, especially since you've done parallelograms at this point. But a couple of things I really want to highlight is for this first one, make sure it's both pairs. So we got to have something where AD and BC are the same and BC and DC. The big part of this is that it's going to be both. Cool. So, and the other part is that we say this is a converse because the opposite side of the parallelograms, assuming that it is already a parallelogram, but when we're going backwards, we got to use that word converse. Alrighty, with the angles, really the exact same idea. It is both pairs. So we got to make sure that those both pairs, boom, boom, and then these two are the same. Gravy. Alrighty, ladies and gentlemen, boys and girls, going on to the diagonals. So in this one, we'll go ahead and draw in our diagonals here, and they got to bisect each other. So remember, bisect just means cut into two equal pieces. So if I put an E right here, that means that AE and EC are the same, but they are not necessarily going to be the same as DE and EB. Those are going to be, a little bit different. But they got to bisect each other. So it's not going to be one set that's bisecting, but they both have to bisect to make sure it's work. So to start off, these four or these top three have been basically both. And that's important to mention because we do get one example, and that's this last one where it is just going to be one pair. Now, I do want to say it's opposite sides, so they can't be neighbors, okay, or what we would call adjacent. So it'd be something like AB and DC, or AD and BC. So where for congruent, we'll give them a tick mark. We're good with that. And remember, this arrow right here means parallel. So I need to have information that these are going to go ahead and be both congruent and parallel. So I do want you to remember that this right here means parallel. It's worth repeating. I know you guys know this. And then obviously our tick marks, that's going to go ahead and mean, let me try to make an arrow saying, but that's the idea, is that is going to be congruent because they're not necessarily always the same thing. Alrighty, so these are 5 ways to go ahead and prove it. And we do have 5 ways, so it's important to make sure that we know all 5 of them. So these 4 are going to be the theorems that we just talked about and we just added. And this last one here is the definition of a parallelogram. Okay, so the definition of a parallelogram is that 2 pairs of parallel sides. Okay, so it's not a new theorem, but this is the one where it's actually a definition. So we got to keep that in mind. So again, today is all about algebra, so let's roll into the algebra. So it says find x and y to make this a quadrilateral. So I think we would all assume, to make this easier, is just assume it is a parallelogram and then go to town. But for this to be a parallelogram, we know that these opposite angles need to be the same. So we're going to do 8x minus 8 is equal to 6x plus 14. Don't mind the drilling in the background. And then we're going to go ahead and have these right here. And so that's going to be 6y plus 16, 7y plus 2. So again, we need to have both of those, so that's why we're doing both sets. So when I bring this 6x over, I'm going to get a 2x. And when I bring that 8 over, we're going to get a 22. So x is going to be 11. Boom, shakalaka. And then on this other one, we'll bring this 6y over, and I'm going to get a 1y. Bring this 2y over, and yay, that's a little less math, so it's 14. So that's x and y to make those opposite angles the same. So now let's work on the opposite sides. So that means this side over here and this side over here have to be the same. So 2x plus 3 is equal to x plus 7. So then we'll go ahead and bring this x over, and I'm going to get x. Bring this 3 over, and I'm going to get 4. Easy peasy. And since it's not asking for what the side length actually is, once we find our x, we're good to go. And then last but not least, let's take care of these y's. So we're going to get 3y minus 5 is equal to y plus 11. Bring this y over, I'm going to get 2y. Bring that 5 over, I'm going to get 16. Divide both sides by 2 to isolate our variable. And y is going to be 8. Done. So you can see the algebra is pretty easy. There's only one thing that might get a little tricky, and that's if we have stuff where you have x and y's on the same sides. And that's what we're going to have on this one right here. So what you're going to do is we're going to treat it exactly like number 2 and set it up. So we'll say that those two are the same because our opposite sides. So 2x plus 4y is equal to 6y plus 1/2 x. All right, so what I'm going to go ahead and do is solve for one of these variables so then I can plug it into the other one. And it doesn't matter which one you do, but it does help getting some of your variables the same. So what I'm going to do is, because I have a 1/2 x, I'm going to multiply every single thing by 2. So to the half, to the 6, to the 2, and to the 4. So we get 4x plus 8y is equal to 12y plus x, because just half of that's going to be x. And then I'm going to go ahead and just bring all of my x's to one side. So when I subtract an x, we're going to get 3x plus 8y is equal to 12y. And then I'm going to go ahead and minus my 8y from both sides. So I right now have 3x is equal to 4y. Now, normally, I would tell you to divide both sides by 3. That makes kind of sense. But right up here, do you notice that this is a 3x right there? So if I look at this sides right here, because we do know that 21 is equal to 3x plus 3y, I already have a 3x right here. And what is 3x? The exact same thing as 4y. So I'm going to use my good old friend substitution to substitute in for that 3x of 4y, because they're the same. We said that they're the same right here. So now when we do that, I have an equation with just y's. And when you have an equation with just y's, that makes our life a lot easier to solve. So I'm going to get 21 is equal to 7y. And so obviously when I divide both sides by 7, we're going to get y is equal to 3. Good to know. So let's take that back in there. Now you could, if you wanted to, if you're a glutton for punishment, you can go back all the way to the top here and solve. And you could, that's doable. But I'm going to say that's a bad idea. So let's erase that and let's go to this equation right over here. That's going to make this a lot easier, and it's still mathematically equivalent. So 3x is equal to 4 times 3, because we know that y is 3. So 3x is equal to 12. So x is going to be, not 3, excuse me, x is going to be 4. There we go. Alrighty, easy peasy lemon squeezy. And you could plug it back in to go ahead and check to make sure your work is correct. But ladies and gentlemen, let's move on. Now I do want to make one thing. You could have started with these two. You didn't have to start with the top. It's up to you. Alrighty, so our next one here is to justify that this is a quadrilateral, but what we're going to do is say that it's a quadrilateral by, I'm going to pause this here. Sorry, I had a panic attack thinking that I didn't record anything, so I just wanted to make sure because I didn't see a little countdown here where I normally see one. All right, so first we're going to go ahead and plot these points. So we have A, which is negative 2, 5, 1, 2, 3, 4, 5. So that's A. And then B is 5, 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Cool. So there's B. And then C is going to be 8, negative 1. So 1, 2, 3, 4, 5, 6, 7, 8, negative 1. There we have C. And then we have D is going to be negative 1, negative 1. Alrighty. So negative 2, 5, 5, 5, 8, negative 1. And then right here we have negative 1, negative 1. All right, so if we look back at our directions say determine whether this figure is a parallelogram. And our directions say to use the slope formula, okay? So slope, we could do as y2 minus y1, x2 minus x1, or we can call it the change in y over the change in x, or simply rise over run. Okay, and I'm a fan of rise over run, especially when it's already graphed out. So the first thing we're going to go ahead and take a look at is, does it look like a parallelogram? And the answer is no. Clearly this doesn't look like a parallelogram, so it's not. Okay, but let's go ahead and prove that, because it does say graph and prove. Okay, so what we need to do is, the definition of a parallelogram means it's going to have two sets of parallel sides. And to review, when you're parallel lines, that means you're going to have the same slope. So let's find the slope. So from A to B, clearly it's sideways, so that's going to be no rise over, doesn't matter what our run is, because that's just going to go ahead and become 0 anyways. And then we have the same thing down here. So this is 0. And then if you actually want to count and make it 9, it's not going to change anything. It's still 0. So the good news is I have one set here that is in fact parallel. Let's find the other one. And as a remember, you always go from left to right. That's how we read, and that's how we plot. So this is going to go down 1, 2, 3, 4, 5, 6, 7. So I went down 7. So I'm going to make that negative over 1. So that's my slope there. So in this next one, I went down 1, 2, 3, 4, 5, 6, 7. Good so far, but I went over 1, 2, 3. So clearly, those are not the same slopes. If we can go ahead and highlight those in yellow here. So that's why we can say that this is no. But really, just using your eyes could have told you that in the first place. But since it said to justify our answer, now we're justified. All right, the next one that you're going to possibly see is the distance formula. So let's get that distance formula up here. So I'm going to go x2 minus x1 squared plus y2 minus y1 squared, square root of the whole kit and caboodle. So we're going to be using that. And since I'm trying to find the distance, I'm going to go ahead and have to do this 4 times. Okay, it is what it is, but let's go ahead and see if we can plot this and see if we can find a shortcut here too. So we have 2, negative 4, 1, 2, 3, 4. So that's Q. And I have 4, 3, 1, 2, 3, 4, 1, 2, 3. That's going to be R. And then 1, 2, 3, 4. Excuse me, I'm doing the wrong one. 1, 2, 3. And then 1, 2, 3, 4. S. And then 5 would be 1, 2, 3, 4, 5, 1. All right, so here is our parallelogram, in theory. Now it looks like a parallelogram, so I'm feeling good. Now, if it didn't say use the distance formula, I would go way back to the slope, because the slope is a lot easier, okay? But what we need to basically prove is that ST is congruent to QR. And so congruent, that would mean they have the same length or the same distance. And then I'm going to go ahead and do the same thing with SR. Needs to be congruent to TQ. So once again, the same distance. All right. So the good news is if this work or this doesn't work, I can just stop and I'd say I've proved it, doesn't work, we're good. Okay. If it doesn't work, if it does work, then we got to keep going to prove it. So ST. So I'm going to go S to T. So x1, y1, x2, y2. So negative 5 minus a negative 3. All that squared plus negative 1 minus 6 squared. And that's going to be equal to, hopefully, QR. So x1, y1, x2, y2. I'm going to do that since it's right here. It doesn't matter if you make this x1 and this x2, we'll get the same answer. So we'll do 4 minus 2 squared plus 3 minus a negative 4 squared. Alrighty, so we got to make sure our negatives are all in order here. So this will be negative 5 plus 3 squared, which is going to be a negative 2 squared, which is 4. And then this will be a negative 7 squared, which is going to be 49. When I add those together, I'm going to get 53. Now, we don't have to break that down, okay, because we're just trying to prove that they're the same distance. So our goal is that this is also 53 right here. So let's take a gander. So 4 minus 2 is going to be 2 squared plus a negative, and negative is going to be a positive. That's 7 squared. So 4 plus 49, yay, square root 53. So we've checked off that those are indeed congruent. So now we have to do the other two. So I'm going to erase this, and I'm going to erase this. You can go back if you need it and hit the rewind button here on the YouTube. But just in the essence of space here. So SR, so we go x1, y1, x2, y2. Again, it doesn't matter which one is x1 and y2 as long as you're consistent. So we'll do negative 3 minus 4 squared plus, and this will be 6 minus 3 squared. I need to move that over. Why am I? So negative 3 minus 4 squared plus 6 minus 3 squared, square root of the whole thing. And that needs to be equal to, this will be x1, y1, x2, y2. So negative 5 minus 2 squared plus, and this negative 1 minus a negative 4. Got to make sure I put in my negatives there. Alrighty. So if we take a gander here, I'm going to get negative 7 squared, which is going to be 49, and 6 minus 3 is going to be 3 squared, which is 9, and when I add those, that's going to be 58. So my goal is that I get 58 over here. So negative 7 squared plus, and let's see, this is going to be a negative, and negative is going to make that a positive, so it's a positive 3 squared. So 49 plus 9 is 58. Yay, check. So it is a parallelogram because these opposite sides are the same, because we proved that using the distance formula. Alrighty. Well, you guys have a wonderful day. Thank you for watching, and we will see you next time.